Hello, everyone. Today we're going to look at another type of electrophilic addition called hydration reactions. Hydration reactions are a specific type of electrophilic addition in which we add a water molecule to an alkene to produce an alcohol. Um, Note the name hydration um, has that uh, root word hydro, meaning water. It's very similar to hydrogenation, which has the root word hydrogen, means to add hydrogen. Um, so try not to get those confused. But let's have a look at the mechanism for a hydration reaction. And let's start with a basic alkene. Okay, so here I have drawn 2-methyl, 1-propene. We're going to add water to that. These reactions, though, typically are done in the presence of an acid catalyst because rather than just adding a water molecule, this reaction is going to actually start with a hydronium ion, or H3O+. Water is technically an electrophile, but it's a weak electrophile. It's also a weak nucleophile. Hydronium, or H3O+, on the other hand, is positive, so it's a strong nucleophile. No, sorry, strong electrophile. And it's more readily attacked by electrons. So here, we have our double bond is going to be what does the attacking. So it attacks one of those extra protons on the oxygen, which breaks the bond that hydrogen had with the oxygen. Okay, this is going to end up transferring the positive charge that was on the water molecule, or the hydronium ion, onto the alkene. So this is going to be a slow step because it involves the formation of a carbocation. Carbocations are not very stable, so this reaction is energetically unfavorable because it involves the creation of a high energy intermediate, this carbocation. The other product here is just water. Okay, so here's our intermediate. Now this intermediate, being positive, is open for being attacked by any nucleophile that comes by, and in this case it's going to be the water molecule. One of the lone pairs on a water molecule can attack that positive carbon. Okay, this step will happen very quickly. Definitely a fast step. No bonds are being broken in this reaction, so it effectively has no activation energy, other than that the molecules have to bump into each other in the right orientation. The next product that would form here would be not quite our final product, but just about. CH3, CH3, and OH, right? So see if you can tell where that positive charge went. Okay. Hopefully you're able to tell that it is now on the oxygen that has 3 bonds. Remember, oxygen usually only likes to form 2 bonds in order to complete its octet. Okay, so this is also an unstable intermediate. It will produce our final product pretty easily, though, once it bumps into a water molecule that can take that extra hydrogen off of the oxygen. Okay, I should really have drawn this that line coming from the O, not the H, because oops. Right, because it is the O that does the attacking. The lone pairs on the O, not the hydrogen. There we go. Gives us our final product, which in this case, I'm going to draw it a little differently. Draw it sideways. Okay, so this product would be 2-methyl, 2-propanol, right? And again, yeah, this last step would be fast. When we talk about reaction mechanisms, we generally just call one of the steps slow. So whichever step is the slow step, every other step is just. So I want you to notice that the first step involves the formation of a carbocation, which I said is an energetically unfavorable step. And this example that I've drawn involves a tertiary carbocation forming. Remember, we know that because this carbon is bonded to 3 other carbons. And tertiary carbocations are the most stable carbocation that could form. So this would form more readily than a secondary carbocation, meaning this reaction would happen faster than if it were producing a secondary carbocation. And our primary carbocation wouldn't really form readily enough for it to be a good reaction to include in a synthesis pathway that you're trying to make. So this is generally not the proper reaction to use if you wanted to make a primary alcohol. Note, tertiary carbocations make a tertiary alcohol. So this is better for making secondary, tertiary alcohols. It could be used to make ethanol from ethene, and in industry, a similar reaction is used, but the conditions required to do so are a lot higher than what we would use in a laboratory, and that's pretty much the only exception. But we'll look at some other reactions that can be used to make primary alcohols. One other note, this reaction follows Markovnikov's rule. Okay, if we were looking at our H2O, right, Markovnikov's rule states that the hydrogen that's being added is added onto the less substituted carbon in the double bond. In this case, we have 2 carbon in our initial double bond. I'm just going to number them. Carbon's 1, carbon 2. And carbon 1 has 2 hydrogens to start, while carbon 2 has no hydrogens. So we would say carbon 1 is the less substituted carbon because it only has a single other, like a single non-hydrogen entity bonded to it, while carbon 2 is actually as substituted as it could be, having no hydrogens. So that hydrogen gets added on to carbon 1 in accordance with Markovnikov's rule, and the OH is added on according to the more substituted carbon. I would say, as far as reaction mechanisms go, this one is relatively simple, relative being the key word. I don't really think any of these mechanisms are that simple, but I say it's relatively simple because it's very similar to the reaction we just learned. The electrophile, which in this case is our hydrogen, okay, the electrophile was added on to the less substituted carbon, and our nucleophile, which we could think of as the OH, or the OH minus if you want to think about it that way, is added on to the more substituted carbon. I said if you want to think about it that way, there is no OH minus in this mechanism. It's happening in acid, but it's one way you could think about it. So this is very similar to the addition of HBr or HI to a double bond. A little bit extra steps there because you've got that water being added on that's protonated and needs to be deprotonated by water, but it's pretty similar. So let's show a practice problem. Okay. The practice problem is to draw a mechanism showing the major product for the following reaction. Okay. So here I've got 3 methyl, 1 butene. Okay. We're going to react that with water and an acid catalyst. Okay. So want you to, if you want, you can pause it, see if you can do this on your own. Okay, but we're just going to get right into it. Okay, so the first thing we're going to start with, we've got our alkene. It's reacting with H2SO4. Okay, So H2SO4, we draw like so. If you want to draw it a little bit simpler than this, that's fine. I'm just going to show all the bonds. Okay. Specifically, I want to show the bonds that are involved in this reaction. Okay, but our double bond here is going to attack our partially positive or electrophilic hydrogen. And when it does that, hydrogen gets kicked off of the oxygen. Okay, so there's our first part of this reaction. That's going to end up producing, I'm just going to draw this new hydrogen in red so that you can see where it's going. Forming our carbocation. So this is going to be a secondary carbocation. Right, according to Markov-Nikov's rule, the primary carbocation would be higher in energy, it would be less likely to form. Okay. This problem is a little bit trickier than you might expect because we have carbocation, a secondary carbocation, I'm going to label that, next to a tertiary carbon. Anytime you have a carbocation next to a similarly substituted or more substituted carbon, what's possible? Rearrangement is possible. Okay, so in this case, we can have a hydride shift. Okay, so it's neighboring hydrogen on that tertiary carbon going to actually shift over, forming a tertiary, a new tertiary carbocation. Okay, that's more stable than the previous intermediate that formed. Okay, I'm just gonna draw those hydrogens. Actually, I'll put that on the beginning one too, just so that you can track where the different hydrogens are coming from. Okay, so that's a hydride shift because hydrogen was moved in order to produce a more stable carbocation. And from here, we're simply going to see the reaction mechanism follow as it was in the previous example. So we have a carbocation that's going to get attacked by a nucleophile. Remember, nucleophiles are Lewis bases. Sulfuric acid is not a nucleophile. Okay, but this is where H2O comes in. Okay, H2O is going to attack that carbocation, right, and give us our positive intermediate. I'm going to leave the hydrogen, those extra hydrogens out of here. Now they're not going to do anything else for the rest of this reaction. Okay, that positive charge is going to be taken away by an additional water molecule reacting with it, taking one of the hydrogens away from the oxygen. Okay, there you have it. We end up getting a tertiary alcohol from our product, or from our initial alkene that didn't actually have the double bond on any tertiary carbons, okay, due to rearrangement. Okay. So one other mechanism that produces alcohols from alkenes that you should be aware of is called oxymercuration demercuration. I'm going to write that down. That's a mouthful. Oxymercuration demercuration. Okay, wish there was a shorter way to say that. This is a two-step reaction. The first step is called oxymercuration, and the second step is called demercuration. But this basically uses a molecule called mercuric acetate, which, as you may have guessed from the name, contains mercury. bonded to acetate. Mercury actually has a 2+ charge and acetate has a 1- charge. So it's going to bond to 2 acetates. Mercury is kind of an unusual metal, definitely unusual because it's a liquid at room temperature. It's also a very unsafe metal, and one of the products of this reaction is mercury metal. So definitely not something we would do in a high school laboratory, something that can be done at the industrial level, but probably not even something you would do at college just due to the safety concerns of using mercury. But still, it's a useful mechanism, or rather, it's a useful reaction to understand. This uses mercuric acetate along with water. Okay, so we're not using H2SO4 here, and we're using THF as our solvent, a tetrahydrofuran. Okay, it's unreactive in this case. As our first step to do the oxymercuration, and this is going to add an OH minus, or an OH group, I should say, to the more substituted carbon and double bond, which follows Markovnikov's rule. It also adds a mercury to the double bond in place of where the hydrogen would have gone. What's noticeable, or what's notable about this reaction is that the mercury that's added, it stabilizes the carbocation intermediate, which prevents rearrangement happening. So if we were to look at the previous example, okay, the intermediate that actually forms, right? So if we look at our previous example, like I said, rather than adding an OH and a hydrogen, we add an OH we're going to add an OH and a mercury. That's the oxymercuration, demercuration. Or sorry, the oxymercuration. The demercuration part is what removes that mercury, replaces it with a hydrogen. That's done using sodium borohydride. Okay, followed by hydroxide to deprotonate it. So, okay, so this happens in 2 steps. Right, those 2 steps actually could happen in the same reaction vessel. But like I said, the notable thing here is that the mercury, when it bonds initially, it stabilizes the carbocation, preventing rearrangement. So again, if we look back at that previous example, we would not get this as our major product. In fact, we wouldn't get that as at all. We would get secondary alcohol as our product for using oxymercuration, demercuration. So it's a notable one to remember, just for the fact that it's able to avoid rearrangement. And if we're using complex substrates in which rearrangement is possible, this can be very useful. I'm not going to get into the mechanism. It's very interesting. It's in the textbook. You wanted to have a look at it, but I would like for you to understand the mechanism for the more basic addition of water with an acid catalyst. But for this one, just note oxymercuration, demercuration, okay. No rearrangement. Okay. Otherwise, the products are very similar. They both follow Markovnikov's rule. Okay. So that's all. If you have any questions, please leave them on Google Classroom. Have a good one.